This is another perspective to mathematically describe the change in heat in a body. Unlike before, when we looked at the change within the body over time, we now look at the flow across the surface. The total heat flow can be in terms of an integral of some quantity. So if we have a box like this, and there's a surface on this box, so the whole surface is the domain of our integral. Now we have to talk about heat flux. When we talk about a flow, we want to quantify a quantity that has a direction. This is what heat flux is about. Now this is a formal definition as in fluid mechanics. Keep in mind the word flux is different now. So again, refer to the BCE book about this. A flux Q is defined as negative gradient of temperature U times the heat conductivity K. As before, U is a scalar field. So why the negative sign? Think about the heat flux as the reverse in temperature difference. For example, in 1D heat propagation, Q is simply negative K du dx. Now, if you have a uniform U, i.e. uniform temperature, then Q is 0. So, no heat flow. If we have temperature variation in the bar, say one side is cold and the other is hot, and now if I plot the temperature like this, du dx is just the slope and it's positive. But we know heat travels from hot to cold, so it's the opposite of the direction of the gradient. And that is why we have the negative for the heat flux. Now looking back at the 3D case like this, Q is a vector field. Think of it like a density of the heat that flows per unit area. So again, we have this Q equal to negative K gradient times gradient of U. So we have the Q vectors all over the surface. Again, it's a vector field. Now, the total or net heat flow is the surface integral. This is exactly as we did before in the first or second lecture. Again, to remind you, we are using different definitions of flux. We now equate the two statements. So we're now combining these two perspectives. The first one from part 1, and now we have another one looking at the surface integral. So what we have here is the left hand side equals to right hand side. So the right hand side is a change in total heat. What we call delta Q, the big Q inside B, and the left hand side is the net flow of heat on the surface S. We can do this by conservation of energy. See now, whatever heat flow change at the surface is balanced by the change in heat content inside the volume. You need to be careful here. This is not yet the Divergence Theorem. This seems to match the Divergence Theorem, but surface integral relating to volume integral. But if you look carefully, it's not the same. In the divergence theorem, we relate the vector field u to its divergence. The right-hand side is not divergence of q in this case. So now we actually apply the divergence theorem. It becomes like this. So we have the q as vector field, and then the div of grad u is div of q. Next, we equate the right-hand side that we got earlier with the one that we have now. This is just a basic algebra operation. So this is a form from part 1. So we have the integral there, and we bring it here. So gather both terms on one side, combining the integral. Then the whole integral is 0 only if the terms in the integrand is 0. So we arrive at the heat equation, finally. Now the final form is just about combining the material constants. When we combine K, rho and sigma like this, we get alpha, which is called thermal diffusivity. Finally, now we have the heat equation as a balance equation of energy. So now we conclude the derivation. Thank you.